All right, let's do the extra practice problems for chapter 12 because we went through it so fast, so it might help. Number 1, using the definition of oxidation state, not the rules we developed, what is the oxidation state of each atom in SiS, which would be silicon monosulfide. And so silicone is in group 4, if you look at your periodic chart. And so it's going to, I'm going to get rid of the dots so it doesn't confuse us. So we're going to have 1, 2, 3, 4 dots. Sulfur is in group 6 if you look on your chart. So it's got 1, 2, 3, 4, 5, 6. Okay, then we start doing this. And I can group those two together. So I can go like this, 1, 2. But when we look at this, this only has 3, but this has 4. So I'm going to have this one share. Okay, now it's sharing. Now sulfur has 4 pairs and silicone has 4 pairs. Now we're told by the definition that the most electronegative is going to be the one that gets the atoms. And, excuse me. The one that's most electronegative is the one that's going to keep the electrons. And if you look at your periodic chart, you'll see, remember, the electronegativity increases this way and this way across the chart. Sulfur is the one that's farthest to the right, so it's the one that's the most electronegative. So that means sulfur is going to keep all of these. Sulfur is going to have 8 electrons. Now sulfur originally was in group 6, so it had 6 electrons. And now when we finish, it has 8 electrons. So its oxidation state is going to be a -2. Silicone, therefore, has to be a +2 so that they will cancel one another out because this has a 0 overall charge, so they have to cancel one another out. That's how you would figure that out. And it is on your test. You need to be able to do that. So remember, count how many electrons it started with, valence electrons, and then how many it ended up with when you get done giving the electrons to the most electronegative in the molecule, and that will be its oxidation number by the definition. And that's what we were told to use there. Number 2, using the rules you learned in this chapter, give the oxidation state for each of the atoms. So the first one, A, is HClO3. If you go through the rules, there's no ions there, so we can't just put those on. +1 for hydrogen is one of the early rules, and Rule 6 says that oxygen gets a -2. So far we have +1 plus whatever chlorine is, plus 3 times -2 is -6, and the whole thing equals 0. So what makes this statement true? This has to be a +5, doesn't it? And so those would be your oxidation states for those. The next one is so simple. I wish they were all that simple. It's 0 because it's in its elemental state, so it's real easy. Well, actually, it's a homonuclear diatomic in this case, but it's 0. Okay, this is a group 1 metal, so it gets a +1 charge. There's 2 of them, so we have +2 plus whatever sulfur is equals 0, so sulfur has to equal -2 to make this true. Let's see, next one, SO4 -2. This is our sulfate ion. Now if we use our rules, the first rule will apply to oxygen, which will be -2. So this is -8. This whole thing has to equal -2. So sulfur -8 equals -2. That means sulfur has to equal a +6. Calcium carbonate. Okay, calcium is a group 2 metal. So if you look on your chart, you'll see that. It gets a +2. We know that Rule 6 tells us to do a -2 there. So far we have +2 plus whatever carbon is minus 3 times -2 is -6 equals 0 because there's no charge on this overall. To make that statement true, carbon has to equal a +4. So that would be the answer. The next one, we have FBr. We know in the rules we're told that this is always a -1, so this has to be a +1. K and O3. This is a group 1 metal. always look and make sure that gets a +1. The next rule, rule 6, tells you this gets a -2. We have a +1 plus whatever nitrogen is, minus 6, because it's 3 times the -2, equals 0. To make this true, that would have to be a +5. That's a 5, believe it or not. And the last one here is H2S. This gets a +1, so this has to be a -2 because 2 times +1 is +2, and so it would have to be a -2. Okay, then the next part, it says for each of the following reactions, indicate whether it's a redox reaction, and then indicate what's being oxidized, what's being reduced, what's the oxidizing agent, what's the reducing agent. This is going to be 0, and this is going to be 0 oxidation state. Those are easy. This one, rule 6, says it's going to be -2. 2 times -2, this is going to be +4. So what we're seeing here is SR went from 0 to +4. That's being oxidized. That number's going up. So that's being oxidized. And so it's the reducing agent. 0, the oxygen, I'm so sorry, went from 0 to -2. It's obviously being reduced, and so it is the oxidizing agent. And that's the information you're supposed to have there. Probably should have put O2 as the oxidizing agent, because remember, O2 was actually on the reactant side, and therefore O2 is the oxidizing agent. I'll show you as we go along, and shame on me. All right, B. Okay, we're going to determine the oxidation states. That one's easy. It's 0. This one is +1, and then this one is -2. So we have 2 times +1 is +2 plus sulfur, minus 4 times -2 is 8, equals 0 for the overall. So sulfur here has to equal +6. Okay, so we got those. Over here, this is a -2, so that's a -4, so this has got to be a +4. Here, this is a -2, so this has to be a +4, because 2 times -2 would be -4, so that'd have to be a +4. Here, these are +1, so this is -2. Okay, let's see. We have carbon going from 0 to +4. So we see something is happening here. So carbon is being oxidized, and therefore carbon is also the reducing agent. Now, hydrogen goes from 1 to 1. So sulfur goes from 6 to 4. Okay, there's a change. So we have going from +6 to +4. This is being reduced. And so what you do is grab what the sulfur's in here, which is on the reactant side, which is H2SO4. Because sulfur is being reduced, this is the oxidizing agent. So you grab whatever that substance is in on the reactant side, and that will be that agent. That's why in the first one I should have put O2 was actually the oxidizing agent, not just O. The next one, this is +1. This is -2, so we have +1 plus N minus 6, 3 times -2, so that has to be a +5. Here, this is a +1 minus 1. Here, this is a -2, so this is a +2. I'm working the rules here, guys. Remember, hydrogen's one of the earlier rules, and oxygen is rule 6. This is a 0, this is +1, so it's a -2. Let's see if we have any changes. Hydrogen doesn't change. Nitrogen goes from a +5, to a +2. There's a change. So we have nitrogen going from +5 to +2. And that is being reduced, isn't it? So we know that whatever it's in, which is HNO3, is the oxidizing agent. Okay, now let's find out who is receiving these. Oxygen's -2, -2, -2. Hydrogen is still +1. But iodine is -1, and here it's 0. So iodine goes from -1 to 0, so it is being oxidized. Therefore, whatever I is in on the reactant side, which is HI, is the reducing agent. And so that's how you would put that. Next one. This is a group 1 metal, so it's +1. And so this is -1. This is a group 2 metal, so it's +2. And so this has to be -2, that's -6. right? So I have +2 plus 2 nitrogens minus, oh, shame on me. That's -6 times 2 is -12, isn't it? Ooh, be careful, because I have 3 times -2, which is -6, times 2, which is -12. So when I put these two together, it gives me -10. So 2n minus 10 equals 0. So n has to be +5, doesn't it? There we go. Okay, so we got that one. That was a little tricky. This is +2 minus 1. Just an ionic compound. We're figuring out the charges. This is an ionic compound. Well, this is ionic. And then once again, we know this is -3. So it's -6 plus 1. I'm going to show you. There we go. So nitrogen has to equal +5. Now we look and we see if anybody's changed. Potassium is 1 each side. Bromide is -1 each side. Magnesium's +2 both sides. Nitrogen is +5. Oxygen's -1. This is not a redox reaction. And you see that because nobody changed. We know this gets a 0. We know this gets a +1. This gets a -2. That's +1 plus nitrogen -6. 3 times -2. So to make this true, it's got to be a +5. This is a nonmetal. And because it's a nonmetal, this is going to be -2, which is -6, equals 0. So this has got to be +3, because it's 2 times Sb to make this true. So this has got to be a +3. That way it's a +6 and a -6. Here, this gets a -2, so it's a +2 plus 1 minus 2. Okay. What we see here is that antimony goes from 0 to +3. So that is being oxidized. So it is the reducing agent. Sb is the reducing agent. Okay. Now, hydrogen hasn't changed. Nitrogen's gone from +5 to +2. So nitrogen has gone from +5 to +2. Therefore, it's being reduced. Its number's going down. And nitrogen is found in this substance, and therefore we will put that as the oxidizing agent. Because whatever substance that's in on the reactant side, that would be our oxidizing agent. Okay, then we're up to number 4. One side of a galvanic cell has copper becoming copper +2. And so you see what's happening here. This is going from a 0 to a +2. So because it's going from a 0 to a +2, it is being oxidized. If it's being oxidized, it's giving up electrons, isn't it? And therefore, which side of the battery gives up electrons? The anode side. So this would be the anode side of the battery, and that's question A. Question B says the electrons flow towards the electrode or away from it. Well, if the anode side is over here, the electron flow is away from it, isn't it? So the answer for B would be away. And then C, the salt bridge. In the salt bridge, are the positive or negative ions flowing toward this side? Well, if this side is being oxidized, it's becoming more positive, isn't it? So it has to have the negative side of the salt bridge to keep it from becoming too positive and stopping the flow. So the answer to C would be negative. Number 5, we're going to make a galvanic cell. Now, every time you're going to make a galvanic cell, I would suggest you draw a very standard anode here, cathode here, draw an electrode on both sides, put your electricity going in this direction. Your salt bridge will go between the two. Here's your liquid in here. You could just put a line across. Okay, that's your standard. Draw that in each one. Shows your electron flow, shows your salt bridge. Okay, your anode, your cathode, that is standard. Now you're going to figure out which one goes where. So the first one, so this is 0, this is +2, this is +3, this is 0. So what we see here is aluminum went from 0 to +3. It's losing electrons. So we know that aluminum is over here, and it started with a solid, so we can put the aluminum solid in the electrode, can't we? And then the aluminum ion is in the solution. And then this guy's going from +2 to 0. It's receiving electrons, and so I'm just going to put, that says aqueous, and that's a solid. We could make this a lead electrode, or you could just put the lead over here in the solution. Your choice. 0, 0, -1, +2. Okay, iodine is going from 0 to -1. It is receiving electrons, and so it is going to be on the cathode side in solution. Calcium is giving up electrons, so it's going to be over here, and it is a solid, so I'm going to put a calcium electrode. You don't have to, but you want to definitely put that all the calcium is over on this side, and that's in solution. Now remember, this side is becoming more positive, therefore it's got to be the negative side of the salt bridge. You don't have to mark it, I just want you to be able to think through this. And this side is becoming more negative, so it's got to be the positive side of the salt bridge to keep this going. And then number 6 asks us to balance the following redox reactions. Here we've gone from a +2 to a 0. Cobalt went from +2 to 0, so it received 2 electrons. 2 electrons. Cesium went from +3 to +4, which meant it gave 1 electron. Now, if this guy received 2, this guy has to give 2. So I need 2 of these, and I need 2 of these. Okay? If I have 2 cesiums, then I have 2 times this, so I have giving 2 electrons, and that's good because cobalt is receiving 2 electrons. So that takes care of my electron issue, balancing my charges. Okay. 0 plus 2, 0 plus 3. Here we have lead going from 0 to +2, so it is giving 2 electrons. Here gold is going from +3 to 0. It is receiving 3 electrons, isn't it? And so the lowest common multiple here is 6. So if we do a 3 on this and a 2 on this, we'll be safe. So we're going to give the golds 2s and we're going to give the leads 3s. And if we do that, then our charges will be balanced. I know it was fast, but study this. Make sure you do all the problems you can. Go ahead, pray hard, take your test, and do the first half of the next chapter. Have a Jesus-filled week.